In this video, we are going to focus on half-life, linked in with the radioactivity topic. Lots of atoms are stable. They have the right balance of neutrons to protons in their nuclei. Stable atoms do not need to change, so they stay the same. Some atoms are unstable because they do not have the right balance between neutrons and protons in their nuclei. The nucleus will change in an effort to become more stable, and we call this change decay. Radioactive atoms decay. Not rotting, not that kind of decay. Like an individual popcorn kernel, an individual radioactive nucleus will change, but we don't know exactly when that particular nucleus will change. It's a random process, this radioactive decay. When a radioactive nucleus decays, the change releases radioactivity. This can be in the form of alpha particles, the equivalent helium nucleus, beta minus particles, the high energy electrons from the nucleus, beta plus particles, positrons, and or gamma rays, the high energy electromagnetic wave. The atom will change into a different atom. It'll have a different atomic number, and that happens when alpha or beta radiation is emitted. You won't always end up with a stable atom, but a more stable atom than you started with. If it's a pure gamma decay, then you do get a more stable version of the same element because you don't have a different atomic number. But I think we need to save that to make our own special video about alpha, beta and gamma in the future. Although each individual atom decays at random, with large numbers of nuclei in any sample, we can see a pattern over time. Before we look at this decay curve pattern, we need to clarify a couple of terms. The activity of a radioactive sample describes the number of nuclear decays that are happening per second. We measure this activity in a unit called the becquerel, given the symbol capital B, lowercase q. A Geiger-Müller tube can be used to detect the activity of a sample. Inside the Geiger counter, there's a gas, and the gas gets ionised by any radioactive particles that enter. This allows a current to briefly flow, and so electronically we measure the count rate or the activity. The number of atoms in the sample affects the activity rate. So if you had 1 kilogram of uranium-235, you'd get more activity than from 1 gram of the same uranium-235 because more atoms means more activity. The time taken for half of the unstable nuclei in a sample to decay is called the half-life. The half-life can be measured in seconds, minutes, hours, days, years, or even millions of years for some radioactive materials. Activity and half-life are linked because the more radioactive nuclei there are in a sample, the more nuclear decays there will be in the same amount of time. But over time, as more and more of the radioactive nuclei have decayed, the sample becomes less and less active. The half-life does not depend on the number of atoms in the sample, so it doesn't depend on the mass of the sample. A particular sample would have the same half-life whether you have 1 gram of it or 1 kilogram of it. Individual radioactive nuclei will decay randomly, but with a large number of nuclei in a sample, we can see a pattern in the way the activity from the sample decreases over time. The time it takes for 50% of the radioactive nuclei to decay into new, more stable nuclei is the same for a particular element. So whether it's 100 radioactive nuclei decaying into 50 more stable nuclei, or 50 into 25, or 80 into 40, or 10 into 5, etc., the time it takes for half the unstable nuclei in a sample to decay is always the same, and this is the half-life of the sample. 2 radioactive half-lives do not make one whole life. I'm going to come back to carbon-14 again. It's a useful radioisotope. It has a half-life of 5,730 years, and it can be used to help us work out how old things are by radioactive dating. Carbon-14 decays into a stable form of nitrogen, and as it does so, it releases a beta- particle. If you started with a 1 gram sample of pure carbon-14, 5,730 years later, you would have half a gram of carbon-14 left, because 0.5 grams would have become nitrogen over that 5,730 years. Then, in another 5,730 years, you would have only a quarter of a gram left, 0.25 grams. Not zero. If another 5,730 years passed, you'd be down to 0.125 of a gram. Yes, an eighth. That's right. Etc. This seems like a good time to have a pause in the video. So try this example and see how you're getting on with these ideas of half-life. How did you get on? I worked out that 1.5, if I doubled it to 3, then back in time I'd have been through one half-life. 3 to 6, another half-life. 6 to 12, another half-life. And 12 to 24 means that the isotope has been through 4 half-lives. So I take the value and divide it by 4 to work out that each half-life must be worth 5,730 years. Half-life can be found using a graph. You choose a starting point on the y-axis and you note the time on the x-axis. You halve your starting point on the y-axis and note the time from the x-axis. The difference in time is your half-life. So I've done 80 to 40, but I could have done 40 to 20 or 50 to 25. All would have given me the same result. Just beware. The less atoms there are left, the less reliable the data is, because this is a probability curve for a random process. Theoretically, it should never actually reach 0. The most common way to model half-life is by using coins or dice. With coins, there's a 50-50 chance that they'll land on heads or tails. So using a large number of coins, we can represent the nuclei in a radioactive sample like carbon-14. Heads, carbon-14. This nucleus is still unstable, still radioactive, and so I need to throw that coin again in the next round. Tails, nitrogen-14. The nucleus has decayed, it's now stable and needs to be removed from the model. Each time the coins are thrown, they land and one time interval has passed. With dice, you can vary the probability to model different radioactive samples. A short half-life, you increase the possibilities. So radon-222 with a 3.8 day half-life, you might remove all the 2s, 3s, 4s and 5s and only leave the 1s and 6s as the undecayed radon-222. To model a longer half-life like uranium-235 with its 700 million years, you might only remove the 6s. When you plot the results from your modelled sample, you will find that same decay curve shape and the same half-life for your model in different places on that curve. But the gradient would be steeper for shorter half-lives on the same time-scaled x-axis. Remember, you need a lot of coins or dice. The model is less reliable with smaller numbers. Never start with less than 100. You can judge the reliability of your data by finding the half-life in lots of different places on your produced graph. If it's the same, it's a good model. Let's summarise all the ideas from our half-life video. Radioactive elements have unstable nuclei. An unstable nucleus will decay into a more stable nucleus, emitting radiation. This radioactive decay is a random process. Over time, the activity of a sample in becquerels will decrease, but the time it takes for half the unstable nuclei to decay will remain the same, the half-life of the sample. Different radioactive elements have different half-lives, from fractions of a second to millions of years. Half-life can be found using a decay curve and used to predict the activity or the amount of a sample over time, either back in the past or forwards to the future. Coins and dice can be useful in helping us model radioactive decay, as long as we use enough of them. I hope the videos helped you revise half-life, because you know that.
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.